Hey guys, this is Angel, and in this playlist we're going to be discussing Newton's laws of motion. I believe this should be week 5 of your course, if we're keeping parallel with you. And in this first video we're going to discuss Newton's first law of motion, which reads, an object in motion will remain in motion unless acted upon by a large enough force, or also an object at rest will remain at rest unless acted upon by a large enough force. So in one word, this is called inertia, an object that stays at rest for eternity unless acted upon by a force is in a state of inertia. And an object that is in motion and that will remain in motion for eternity is at inertia. And inertia will be broken when a force is large enough to get it to start moving in either an opposite direction or to just get it to move. And so I've drawn out 3 different scenarios for you so that I can give you examples of inertia and when inertia is broken. And so the first scenario here, we've got a ball whose velocity is 0 meters per second. That means that this ball is not moving. It's on a flat surface, so there is no acceleration in the upward or downward direction, and there's nothing acting upon it. And so for the rest of eternity, this ball is going to remain at rest unless there's a large enough wind or somebody comes and kicks the ball to break its inertia. And so that is inertia at rest. And the second scenario, we've got the ball moving down an incline. Now I've drawn it for a different color just to show that it's a different scenario. And this ball is moving down an incline with an acceleration that is equal to the sine of the force of gravity, that's g. Now we're not going to get into how we calculated that just yet. We're going to get into that a little more in a second video where we discuss the second law of Newton, in which we discuss a little bit more about body diagrams and how we calculate certain forces using those body diagrams. But in this case, I just want to show you that this ball is not in inertia. It's broken. It's inertia because it is accelerating. So it went from being at rest at a velocity of 0 and has come down this incline with an acceleration, and because it's accelerating, its motion is being broken. So I want you to think of it as a ball that is moving 3 meters per second. If it is in inertia, it's going to continue 3 meters per second for eternity. However, if it goes from 3 meters per second to 4 to 5 to 6, then it is no longer in inertia because that motion is being broken and being increased due to the acceleration. In this case, there is nothing physically acting on the ball. Instead, it is a field force that is making the ball move in an acceleration. That field force is due to the force of gravity from the earth. Now, when this ball eventually reaches down here at the end of the incline, it's going to reach a final velocity. That final velocity is the velocity that this blue ball, which is still the same ball, just a different color, this blue ball is traveling, and this blue ball is also stated to be on a frictionless surface. Now, I put here that sometimes it's not frictionless. The surfaces aren't frictionless, and that's where we're going to discuss static and kinetic friction in the following part of this video. But in this case, that final velocity is the same velocity that this blue ball is going to travel for the rest of eternity until it is acted upon by a large enough force. So maybe it's going to hit another ball, and that's going to cause its motion to change. So it's going to break its inertia. Maybe it's going to hit a wall, and then its motion is going to be acted upon and cause it to stop. That's also breaking the inertia. Or maybe if it did have friction, then the cement would eventually slow it down because it's giving it a force in the opposite direction that is causing it to slow down, again breaking its inertia, because slowing down is accelerating in the opposite direction, in the negative direction, we could say. So I want to move on to a problem that briefly introduces a static and kinetic friction, and we're going to talk about how that applies to the first law of inertia. So in this scenario, we've got a 50 Newton force that is being horizontally applied to a wooden 15 kilogram box on a wooden surface. The coefficient of static friction is 0.3, and I want you to notice that it doesn't have any units, and the coefficient of kinetic friction is 0.2. So when this wooden crate is sitting on the wooden floor, then it is in inertia. It's at rest, nothing is acting upon it to cause it to move until this 50 Newton force is applied right here. the first question asks, is the force sufficient to get the box moving? And this is where we have to solve for our static friction and compare it to the force that's being applied. Now, the difference between static and kinetic friction is that static friction is what is required, is the force required to get it to move. So get moving. And kinetic friction, the coefficient of kinetic friction is going to be smaller than the static friction coefficient, because once we get it moving, it's easier to keep it in motion than it was to start getting it to move. And so if even a piano on wheels, let's say, in my job, we move a piano every now and then. And so that piano requires a pretty good amount of force to get it to start moving. But because it's on wheels, once we do get it moving, it becomes a lot easier to keep in motion than it was to get it moving. And we're going to discuss why that is here in this scenario. And so static friction is the friction that we need to overcome to get it to start moving. And then kinetic friction is the friction that we need to overcome to keep it moving. And if we've got it to start moving, we'll be able to keep it moving, but there is going to be a force difference that's going to cause a difference in the acceleration or the net force that is being experienced. And so we're going to talk about that right now. So is the force sufficient to get the box moving? Well, we need to solve for this static friction force, because we know that we've got a 50 Newton force here. So how do we solve for static friction? So in your equation sheet, or it may not be, but I'm going to go ahead and show you that static friction is solved by multiplying the normal force times the coefficient of static friction. And so we've got a 15 kilogram box, that's its mass, so its weight must be 150 newtons, and the normal force, because this is on a flat surface, is also 150 newtons. So we're going to do force static friction is equal to 150 newtons, and then the coefficient of static friction we mentioned is 0.3. And so we want to do as much mental math as we can, and so I'm going to find the 1/10 of 150 newtons, which is 15 newtons, and then multiply that by 3, so that's going to be 45 newtons. And just as we try to do as much mental math as we can, because we're not going to get a calculator on the MCAT. And so we're looking at 45 newtons is the force, and I want you to really keep this in mind. The static force is 45 newtons. That means that we need to apply a minimum of 45 newtons to get the box to move and break its inertia. Okay, so we solve for the first part, and that's 45 newtons. Now let's go ahead and solve for the next part, and that is, what is the net force of the box in the horizontal direction when it is moving? So like I mentioned earlier, it is easier to keep something moving than it is to get it to start moving. And we're going to see that here, because the same equation is used to solve for kinetic friction. And so I'm going to, instead of putting Fn, I'm going to put the normal force directly in there. And then the coefficient of kinetic friction is 0.2. And when we solve for that, we get 30 newtons. And so the kinetic friction force in the opposite direction, we call that negative 30 newtons, is less than the negative 45 newtons that we needed to get it to start moving. Now that we've got it moving, now that it is in motion here, then we only need to push with 30 newtons of force in order to keep it moving. So this means that this 50 newtons, we could actually not have to push so hard anymore. Instead of pushing at 50 newtons, we would need to push at 30 newtons in order to keep it moving. But in this scenario, we're still applied with the 50 newtons, which means that 50 newtons minus the 30 newtons of kinetic friction gives us a net force of 20 newtons. Now, we haven't discussed here in this video the second law of motion, which discusses how net force is proportionate to acceleration. So you may have a bit of a hard time understanding how it is that we got these values, differentiating between positive and negative forces depending on their direction. But you will get introduced to that later in this playlist. And then if you did have a hard time understanding this, come back after you've watched those future videos, and hopefully it'll make a little more sense. So thank you guys for watching. Leave any comments or questions in the comment section below. Make sure to subscribe so that you can stay parallel with our videos as we stay parallel with your class. Thank you.